So here we're going to go through some notes and some hints for doing Taylor series expansions. So I've written out the Taylor series expansion up to the third order term. And what I want to point out is that once you know that this is how you write out the Taylor series expansion, you need to understand what the process of the steps are going to be. So first we're going to take whatever this function f of x is, and we're going to take its derivatives and we're going to put them into a table. Then we're going to add a column to that table where we evaluate the function and all the derivatives that we've got at a particular point. And that's going to give us numbers here. And so the key thing that I want to point out is that in this Taylor series expansion, these things in front of the deltas, these are all numbers. So what you want to do is you want to make a table of the numbers that you're going to put in, and then after you have that table, then you can use the table to put together your Taylor series expansion of the function. So for example, let's suppose that I want to do the Taylor series expansion of f of x, where this is the function sine of x. And so let me suppose that I'm going to do this Taylor series expansion of f of x around x equals 0. So the way I'm thinking about that is I'm thinking of f of 0 plus x, where this x now here is the small thing. So I'm going to first do my process. So my process is to say, well, f of x is the sine of x. So the derivative of the sine is the cosine. The derivative of the derivative, so now I'm going to look at the cosine, take the derivative of that. I have minus sine of x. Then I have another derivative. So I can just keep taking the derivative of the function right above is now minus cosine of x. The next derivative would be the derivative of the cosine is minus the sine. So I can get back to the sine of x. And so I could keep going here. Now I said that I was going to take these derivatives, I was going to take the Taylor series expansion around the point x equals 0. So I'm now going to stick in 0 into these functions. So at 0, the sine is 0. At 0, the cosine is 1. At 0 minus the sine is 0. At 0 minus the cosine of 0 is 1. And then I'm back to 0. Okay, so now I have my numbers. And my goal, here I'm thinking of expanding around the point 0, which is why I put 0 in and got my numbers. And then x is going to be the little distance away. So that's going to be f of 0. So whatever is here is what's going in there. Plus f prime at 0, see that's what's going in there, times x. See the x is what's coming out over here. Plus a half of f double prime at 0. See, I'm again evaluating at 0. Times x squared, whatever I've added there. Plus 1 over, the next term is 6. f3 at 0 times x cubed. I went up to f4 here, so I'll keep going. 1 over 24, the fourth derivative at 0 times x to the fourth power. And I could keep going if I wanted to. So now the key is, though, that I have the table, and because I have this table already prepared, I can now simply start to plug things in. So f at x, or f of 0 plus x, is f at 0. So f at 0 is this number. So 0 plus f prime at 0, that's this number. So that's 1 times the x. F second derivative at 0 is that number there. Again, at 0 times x squared. I have a sixth. The third derivative was minus 1 times x cubed. The next term was going to be 0 again. The next term, by the way, would be 1 over 5 factorial times 1 times x to the fifth, because you'll see there's a pattern here, right? The pattern is I'm going 0, 1, 0, minus 1, 0, 1, 0, minus 1. So if you keep going down here, you keep flipping in your derivatives between 0, 1, and minus 1. So if I work it out, and I just keep the terms that aren't 0, I see that f of x was the sine of x is approximately x minus x cubed over 6. Then I've got 1 over 5 factorial, which is, I think, 120. So that's 1 over 120 times x to the 5th. The next term would end up being negative, and it would be x to the 7th over 7 factorial. The next term in this would be x to the 9th over 9 factorial, and you end up alternating signs. And I use here an approximately equal sign because I didn't write out all the terms. I guess since I wrote plus dot dot dot, I could have used an equal sign there. But if I only keep that number of terms, then I might say it's approximately given by this here. So now, let's suppose that instead of wanting to compute the sine of x about x equals 0, I want to know what is the sine of x near x equals 0.2 radians. So again, I'm going to write down my table. So f is the sine of x, f prime is the cosine of x, f double prime is minus the sine of x, f3 is minus the cosine of x, f4 is back to the sine of x. But now I'm going to put in the value into these functions. So here I have the sine of 0.2 radians. Here I have the cosine of 0.2 radians. Here I have minus the sine of 0.2 radians. Here I have minus the cosine of 0.2 radians. And I'm back to the sine of 0.2 radians. Now, none of those numbers are going to be 0, but the key point is that those are all numbers. Whatever they are, they're all numbers. So if I'm thinking about this as f of 0.2 plus delta, where now x is 0.2 plus delta, say. So I'm thinking the sine of x is f of x of 0.2 delta. So I'm going to have the function, which in this case is the sine of 0.2. Well, let me write down the general formula again. So f at 0.2 plus delta would be f at 0.2 plus f prime at 0.2 times delta plus a half the second derivative at 0.2 times delta squared plus 1 over 6, which is 3 factorial, f3 at 0.2 times delta cubed plus 1 over 24, which is 4 factorial, the fourth derivative at 0.2 times delta to the fourth power, and then that would continue. And so I have here my values tabulated, right? So I'm thinking that I have these as numbers, but I'll just write them in for here, right? So f at 0.2 plus delta then becomes the sine of 0.2, whatever that number was, plus the cosine of 0.2 times delta, plus a half times minus the sine of 0.2 times delta squared, plus a sixth times what I need. I need f3. f3 is minus the cosine of 0.2 times delta cubed, plus 1 over 24 times the sine of 0.2. See, I'm going and picking up whatever the number is times delta to the fourth, and then I could continue that if I wanted to. And so the key here, whenever you're doing a Taylor series expansion, is to first take the function, then write down a table where you take all the derivatives. Just take the derivative, take the next derivative, take the derivative of that, take the derivative of that, take the derivative of that. And then wherever it is you're trying to evaluate the function around, add a column where you pick up those numbers. And the reason you do that is that those become the numbers that you put in all the places. And then you can simply write out your Taylor series expansion somewhat quickly.